show you the syntax of those comparison operators. Now you don't just have to have a single line of text in the indented block, and this will be something you're going to get used to. So if we indent more than one line, then the conditional code is actually these 3 lines. So the idea is you have an if statement, you come in, you do an indent, and as long as you stay indented, you stay in that if block. If it's false, it just skips all of those. So the way this is going to execute, x is 5, we print before 5, is x equal 5, that's the question mark, and that's true. So it's going to run all these, and then come back, and then continue on in the de-indent, so all this stuff is running, right? And then it says x equals 6, well that was false, so that skips all of them. So none of these lines of code run, so these actually don't run, and it says afterwards 6, so that's a mistake. Those don't run right there, okay, because x is not equal 6. Okay? So indentation is an essential part of Python. We use indentation in lots of programming languages, often to kind of demarcate blocks, to show where blocks start and stop. But in Python, it's syntactically correct. You can make an error if your indentation is wrong. After an if, you must indent. And you maintain the indent as long as you want to be in that same if block. And then when you're done with the if block, you reduce the indent. In this rule of indenting, comment lines and blank lines are completely ignored. So we're going to tend to like put 4 spaces. 4 spaces ends up being the normal thing that we do, and you'll see all the code that I write has 4 spaces for each indent. If I go in twice, I use 8 spaces. And we have this instinct of wanting to hit the tab key to move in 4 spaces. Now the problem is that it might look the same on your screen. A tab and 4 spaces might line up the same place depending on how tabs are set. But Python can get confused by that. So we tend to avoid using actual tabs in files. And so most programming text editors, like if you're using Notepad or Text Wrangler, there's a place to set the tabs to say don't put tabs in this document, but every time you hit a tab, move over 4 spaces. And so you hit a tab, but it's like space, 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 space. Now the nice thing about Atom, and this is the text editor we tend to recommend in this class, because it works on Windows, Linux, and Mac, but also because it automatically sets this up. As soon as you save your file with a .py extension, you can sort of hit the tab key with impunity, and everything works perfectly. But the key thing here is that Python insists that you get this right, and if you don't get this right, you're going to get indentation errors, and they're just another syntax error. So if you're using something like Text Wrangler or Notepad, hunt around in the preferences and you'll find something about expanding tabs, or maybe how many spaces each tab stop is supposed to be. And so you check these, and what this really is doing is telling your text editor never put an actual tab in the document, but somehow simulate tab stops using spaces. And so here is a bit of code. It's got a nested block, but it gives you this sense that you have to be very explicit when you're reading Python code of whether the indent is the same between 2 lines, the same, increased or decreased. And so every time you increase it, you mean something, and every time you decrease it, you mean something, and literally if it stays the same, you mean something as well. And so if we take a look at this, here we have a line, and the next line has the same indent. This is an if with a colon at the end, so we have to increase the indent, and now we're maintaining it, okay? So these 2 lines are part of that if, but now we have de-indented. So whether you choose to de-indent this word or whatever, where you do this de-indent affects the scope of how far this if statement lasts, right? It lasts up to, but not including, the line that's de-indented to the same level as the if. Okay, so this is a de-indent. Now we have a blank line, which doesn't matter, and we maintain it. Now we have a for, which we'll learn about in the next chapter, which is a looping structure. Let's do a for runs this 5 times. It has a colon, and it also expects an indented block. Now we have what's called a nested block, where we have an if and a colon, and we go in some more. So this is like 2 indents, right? So these are 1 indent, and these are 2 indents. And so this is a block within a block. And then we de-indent, so that means this print is not part of the if statement, but is still part of the for statement. then we de-indent again, and then that means this print is sort of on the same level as that for statement. So if you start thinking about this, you want to be able to start thinking that these blocks are the start of the block with the colon line up to but not including this line that's been de-indented. So the for goes this far, right? The for goes up to but not including the line that's de-indented. The if goes up to but not including the line that's de-indented. So as you do this, you'll sort of mentally start drawing these blocks, and pretty soon you will start constructing them as blocks. And it takes a while, but doesn't take forever. But in Python, unlike other languages, you have this is very important, and it matters, and you can have syntax errors if you get it wrong, because you're really communicating the shape and structure of your code using these indents and de-indents. We already saw a nested indent. This is a nested if, so you can put an if within an if, and you can go as far deep as you want to go, like Russian dolls. And so here we have x equals 42. If it's 1, we indent 1, and then with this next thing we do, these are at the same level of indent, but now we see an if, and it has to indent further. So this is like 2 in, 8 spaces, and then we de-indent back. Actually, we de-indent back 2. And so if you watch this and you take a look at how this works, it runs to here. Oops, back up. Comes in here. The answer is yes, x is greater than 1. Prints this. Is x less than 100? Well, it's 42, so the answer is yes. So it runs this, and then it kind of continues back to there. And you can also think of drawing boxes around this. This is one if box, and then within that if box there is another if box. And again, it's the indent block up to but not including where the de-indent happens. And this here is like 2 backwards de-indents. So it ends 2 blocks. So 2 blocks are ended by where we place this. We could move this in, or we could move this out. We could have it all the way into here, we could have it to here, or here. And where we put that line depends on how the ends of these blocks are going to work out. So one form of that's a 1 branch if that we just saw, but then you can also have what's called a 2 branch if. And the basic idea of a 2 branch if is that you're going to come in, you're going to ask a question, and you're going to go one direction if it's yes, and another direction if it's no. We call this an if then else. It's kind of like a fork in the road. And the way to think about it is, depending on the output of this question, we're going to pick 1 or 2 of these, but if we pick one, the other one's never going to happen. So it's like an either or. We're either going to go one way or we're going to go the other way, but there is no path where we somehow go boot through both of them. That doesn't happen. And the syntax that we use for this is what we call the if then else. And so the first part is a normal if with an indent, and then we de-indent, and then this is another reserved word, else, with a colon, and then we re-indent. And so this is really end up being part of a whole block here, and the else is the part, this is the part that runs if it's false, and this is the part that runs if it's true. The first branch of the if, the first indented block is what runs if it's true, and the second indented block is the one that runs if it's false. And so here we go, just if x is greater than 2, in this case it's yes, we're going to print bigger, and then we're going to be all done. And so we do 1, and so this one did run and this one did not run. So basically with an if then else, one of the 2 branches is going to run, but there's no case in which both branches run. And again, you sort of draw these blocks around these things mentally, and in this one you sort of take from the if, not the else is really part of the block, up to but not including that print, which is back indented, de-indented back to the same level as the if statement. Okay? This Python is actually one of the more elegant languages, even though after a while this indenting, and when you get too far in, it gets a little bit complex, but this is a good way to visualize this with these indents. Coming up next, we're going to talk about some more complex conditional structures. So welcome back. Let's talk a little bit more about some more complex conditional statements that sort of build on this concept of if and if then else. The first thing we're going to look at is the multi-way branch. And so the idea is it's kind of like the if then else, where you're going to pick one of 2, but now we can pick one of 3 or one of 4 or one of 5. And it introduces a new concept called the LF. The LF is another reserved word inside Python. And the way it works is it's probably best to look at this here where it checks the first one, and if it's a true, then it runs that, and then it's done. It doesn't check them all. It's not like it sees that there are two logical conditions. It actually checks them, the first one, and how you order these matters, as we'll see in a bit. And so if the first one is true, it runs. If the first one is false and the second one is true, it runs this one and it's done. And if neither of them are true, it falls through, and there's an else clause that is otherwise, and it runs that. So basically, it's either going to run one and then skip the other two, or it is going to, skip one, skip two, and then run this one. But it only runs, in this case, one of them. But the important thing is it checks these questions in order. And it doesn't check the second question until it finds that it doesn't check the second question until it knows the first question is false. So if the first question is true, you're done. You're done, and you're done with this. You're done with the whole block at that point. So only one of these three is going to execute in that block. So here's sort of some examples of this. If we, for example, have x equals 0, it's going to come down here. X is less than true. That's true. So it runs this code, and then it skips down to that. And so it's like this, runs that code, and then skips to the end. Okay. On the other hand, if it's 5, then this is false, and it skips that, and it checks this. This is true. It runs this code, and then it's done, skips to the end. It goes like false, true, run, end. And then if x is like 20, for example, it runs, false, false, run the else clause, and you're done. So skip, else, run that code, and you're done. So in this case, we ran that, and we didn't run that, and we didn't run that. Again, one of them's going to run. They're checked in order. These questions are checked in order, not out of order. It doesn't look ahead. It just checks in the order that you wrote it. You're the one that wrote that order. And so there's a couple of variations on this multi-way. You can have no else. You can have no else, as in this case. And this just means that it might not run any of them. In this case, x is 5, so it's not less than 2, but then it runs this one. But if x was like 50, for example, if x was 50, then this would be false, then it would skip, and this would still be false, and it would skip, and neither of these two would run. So if you don't have an else, you're not guaranteed that one of them is going to run, because else is like the catch-all. If the other ones are all false, then the else is the one that runs. Similarly, you can have many elifs, but this is where it's really important for you to make sure you know what order they're being taken in. So I've got, this. If this is true, it runs. It goes all the way to the bottom. If if it's false, 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 true, it runs this one and it's done. If, on the other hand, it looks at it as false, go back. If it runs false, 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 they're all false, then it runs the else. Right? This one has an else. This one didn't have an else. They don't have to have them. The key is you can have more than one of these elifs. Okay? So I got a couple little things. I'll let you pause right now and look at, the question is, are there, looking at the 3 lines or 4 lines of code, x equals something. Are there lines of code that will never execute regardless of the value for x? And I'll let you pause and think about it, and then I'll explain it to you. Okay. Hopefully you paused and thought about it as long as you like, so let me now explain it to you. So we come in here, and if x is less than or equal to 2, it's going to run this first thing, and if x is greater than or equal to 2, it's going to run this, and if neither of those are true, then it's going to run this. Well, the weird thing is, all numbers are either less than 2 or greater than or equal to 2. I carefully constructed this to the point where it would never run this line of code. It is either going to run this one or run that one, but it's not going to ever run this one. So that was kind of like a weird dysfunctional one that I constructed. This other one is a little different. If x is less than 2, we do this. If x is less than 20, we do that. If x is less than 10, we do that. And if none of those are true, we do that. Well, the problem here is between these two lines. The problem is if something's less than 10, like 6 for example, it's also less than 20. So even though there might be values for which this is true, those also are going to have this true. So for something like 6, it's going to run here, and it's not even going to look at this. That's the point. It doesn't even look at this. And so I mean, I could have made this more sensible if I'd have moved this little block of code up to there. So this is where the order in which you choose your questions, the way you put these LFs together matters, because it doesn't look at all of them. It only looks as long as it can. As long as it sees falses, then it keeps on going to the next one. But as soon as it doesn't see a false, it doesn't continue. So the last conditional structure we'll talk about is the try and except structure. And if you know any other languages like C++ or Java or JavaScript, you're like, whoa, that's kind of an advanced concept. But it turns out in Python, because of Python's propensity to throw tracebacks in situations where you kind of would like to recover, it turns out you kind of have to use it a little more and a little earlier in your programming skill. So the problem is what if there is a line of code and you absolutely know it's going to make a traceback, it's going to blow up, but you don't want to blow up. I mean, I don't want to have code blow up. If you're using my autograder and you see a traceback in my autograder, that's kind of like, I consider that a failure. I could put an error like, hey, you entered blank data, or you didn't enter a number, but a traceback, that just seems like I'm too lazy as a programmer. So we as programmers are supposed to anticipate parts of our code that are going to blow up potentially based on perhaps the user's input, and then do something about it. And that's what the try and except are for. It's you take this little dangerous piece of code that might break and might blow up, and you surround it with a try and says this might blow up, and if it fails, run this code down here. Okay, so that's the try, and if you get an exception, the except is kind of like if you get an exception. And the problem is if you are running code, here's a little bit of code, we put hello Bob in, and then we convert it to an integer, and we know from past experience that this blows up. Right? You can't take hello Bob and convert it to an integer. It's just going to blow up. The problem is, and you know, here we are, it says, oh, you blew up on line 2. That's great. And I'm not very happy with hello Bob and whatever. But the important thing is your program stops. These other lines, they don't, oops, these other lines, they don't exist. Right? It doesn't go any further. Remember the traceback is Python is really confused and I don't know what to do next. So Python is just going to be conservative and stop. So Python stops and your program stops. No matter how much error checking you put down here, it doesn't matter because it's gone. It's all gone. And like I said, we take this kind of personally because the code that you write is like you being put into the computer, giving it instructions. And if the code blows up, well, that sort of wipes you out. You're not in the game anymore. You're not able to do anything. So we want to be able to, especially in these situations where we can anticipate that an error that might happen in the normal course of your program's execution might be something that you want to compensate for. And that's what the try and except does. So here's a bit of code for the try and except. And we just have 2 little bits of straight line code. And so we put a string in here that's hello Bob, and then we're going to convert it to an integer. This is the dangerous code. This code in this case with hello Bob is going to do a traceback. And so we say try, and then we indent the dangerous code, and then we add this little except bit. If it works, the except is ignored. If this blows up, it runs the except. So in this code, it's going to come in, it's going to try this. This is going to blow up, but instead of giving a traceback, it's going to say, oh, I've got an available except. I'm going to run this except code, and then I'm going to continue on. And so that prints out first -1. So because we set this variable ister to -1, like a little flag telling us that something went wrong. And then we keep on going, and now we have put in 1, 2, 3, the digits 123, the digits 1, 2, 3, and now it's going to work, but we still have it in a try block, and then this one works, it does not blow up, and then it ignores the except block. So the except block is only triggered when something goes wrong in the code. It is ignored if something doesn't go wrong. So it's like you bought an insurance policy on this line of code, and when things go wrong, your except block springs into action and does whatever it is that you want it to do in the case of an error. Okay, so that's a pretty useful thing. You got to be a little bit careful that you don't overuse it, because if you put more than one line inside the try part and one of the lines blows up, it doesn't come back to the try block. And so in this one here, we have kind of a simple, silly one where we set the string. We're worried about some stuff. Well, the print statement's never going to blow up, so it's a bad idea to put it in try except anyways. Then we do this conversion, and that's the dangerous part. And in this one, it's going to blow up. And so then it's going to go to the except block and then run the except block and then continue. What it doesn't do is somehow go back and finish this. So these lines are gone. So if you look at it like this works. The try starts. Hello. This blows up. It goes to the accept. It runs the accept, and it continues on. Never runs that code. So it's not like you took out an insurance on the whole block. Any of those lines can blow up in the block, but whichever line blows up, that is the last line that's executing in that block. Okay? So you tend to want, in this particular example, you would probably, the print statement would go out there, and this print statement would come down here, and you would only put in your try block the single line of code that you think might blow up, because you kind of know print statements aren't going to blow up. So this is an example that's a more common real-world example where the user is going to type some data. And it's users that get us in trouble. So our program starts by asking the user to enter a number, and we know that this could be dangerous. So we're going to do it. We're going to put the conversion from string to integer in a try block, and we're going to set -1 if that's a failure. And then if it's greater than 0, we'll say nice work, and if it's less than 0, well, not a number. So first time we run this program, out comes enter a number. We type in 42, which is a string. That 42 goes back into roster, runs in here. This runs. It's fine. That becomes a 42 number, so we skip the except block, and ival is greater than 0. We print out nice work, and we skip the else. Okay? So it says nice work. On the other hand, if we run it again, this time, the input says enter a number, and we're silly. We enter the word 42, but in words, 40, F-O-U-R-T-Y. So that's a string, and that goes into roster. And then the execution continues. We run in here, and now this is going to blow up. That's going to blow up. Normally, we would see a traceback right there. There'd be a traceback, but we're not going to because we put this calculation in a try and accept block. It's going to immediately run the accept block, set ival to -1, continue on with the program. See, you are not blown up at this point. And if ival is greater than 0, well, it's -1, so we're going to hit the else clause and print out not a number. So we've done error detection. The user set something that caused a line of our code to kind of blow up, but we put that line in a try and accept block, and so we caught it. And so we dealt with that fact. So in summary, in this, we talked about if statements, we talked about else, we talked about try and accept, how important indentation is to mark blocks where they begin in the end, and an else if and try except. So up next, we're going to talk about loops and iteration. Hello and welcome to Chapter 4, Functions. This is the fourth of our basic patterns. We'll get to iterations next. Functions is the store and reuse. One of the things in programming is that we never like to repeat ourselves. We don't like to, if we have 4 or 5 lines of code and we're going to do the same thing later, we don't like to put the same 4 lines of code in, even if it has to do with reliability. If you find something wrong with those 4 lines of code and you got them 12 different places in your program, then you got to find all 12 places and fix them. So we're like, collect those to one place and then call them and reuse them. And that's the idea of store and reuse. So this is how functions work inside of Python. The first thing we notice is there is a new keyword def that stands for define function. And the def is like an if statement, or we'll see fors and whiles, that they end in a colon, and then they have an indented block, and then the indented block de-indents, and that's the end of the function. And so there's 2 statements make up this function. The key thing that you have to understand and get used to is this def part is actually not running any code whatsoever. It's actually remembering the code, and that's what I call the store phase. The def creates a bit of code and records it like a macro, although it's much more complex than a macro, and it names it whatever you chose. You gave it a name. We named this one thing. And so it, as a side effect of Python reading or parsing these 3 lines, it doesn't do anything, but it remembers. These 2 lines are what you would like to run when you invoke thing. So this is the definition of a function, and this is the invoking of the function. But so this doesn't do anything. So there's no output here from that stuff right there. But then what happens is you invoke it. And this thing looks like it's part of Python, but you in effect have extended Python with your def statement. And so when it sees thing, it goes up and runs your code. And so out comes hello fun. And then it comes back and goes to the next line, does print, so print comes out. And then it goes back and like, oh, this is the reuse part, but we get to reuse it. We define it once and we use it twice. Then it runs this code again and then goes to the next line and it's all done. So this little bit came out twice. And of course this is really simple so that I can fit it on a page, but you get the idea that I don't want to repeat. This might be, 15 to 100 lines of code, and I don't want to type those over and over again. So I say, hey, store these in a name that I choose, and then when I invoke them, bring them back and then run them again. Okay? So that's the basic idea. We actually have already been using functions from the beginning. The print is a function, right? Print is a function. Every time we see print, P-R-I-N-T, parenthesis, and then we have some stuff in here, we are calling the print function. This is the syntax with two little parentheses, is the syntax for functions. And so input's a function, type is a function, float's a function, int's a function. All these things are built-in functions that come with Python at the moment that we started. I mean, we installed Python and these came along. And then there's other functions that we define and use, and that's what the def is for. And in effect, we can create new reserved words of our own making that extend the Python language after we define the function. So it's just this bit of reusable code that takes some arguments. We haven't seen any with arguments. There's a little parenthesis, and we'll see how that works in a bit. We define using the def keyword, and then we invoke it. There's the defining phase, which actually doesn't run the code, it just remembers the code, and then there's the invoking phase. You define it once and then invoke it one or more times. Calling the function or invoking the function, we think of those two things as the same thing. Call, invoke, or just the terms we use. Most people just say call the function, but invoking it is a perhaps more descriptive way to think about it. So here's an example of a function. It is built into Python. It's called the max function. And we can pass some parameters into the max function. So we pass the hello world string. Now, like much of Python, max knows what kind of thing is being passed into it, and it knows that it's looking for the largest character, the lexicographically largest character, and in this case, it scans this little, that's inside the max code, it scans through and finds the largest character. So apparently, lowercase letters are higher than uppercase letters because in English, we get back a W. And so this is what's called the return value. So this is an assignment statement. Let me clear this and start over. So this is an assignment statement, so it has to evaluate this right-hand side. And a function call is nothing more than like x plus 1. It's something to evaluate. It runs the function code, passes in this argument, and then this residual value, this is called the return value, we'll look at this in more detail, becomes the result of this little bit in the expression, and there's nothing else. We could have, w plus 1 or something, and then the w is what's stored into big. Okay, so we print big, and big is a variable that has the letter W inside of it. And then we ask what is the smallest, and that finds the blank, and so we get a blank to see this. There's a min function and a max function. Both of these are built in. These are built-in functions. They're always there for us. Okay, so here is another example of the max function, and so we can think of this as invoking or calling this function as this right-hand side is being evaluated. We are passing this variable in, and there's some code in here, and it's going to do some stuff, yada, 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 and then it's going to give us back a bit of stuff, and that's its return value, and then that goes up into the big, right? And so that's how this works. And so this is actually built in or burnt in, I guess I can't draw. And so you can think of this as sometime a long time ago when Python was being first formed, somebody wrote some code. And it's got some stuff in it. It's got a little loop that reads through all the